Okay, so Assalamualaikum and a very good afternoon to to all our colleagues in Ghana and good evening to our colleagues in Malaysia. So I'm Dr. Afika from University Science Malaysia. We are happy and excited tonight to have Justice Moses with us to join our webinar tonight. So Dr. Justice Moses is currently a lecturer at the Department of Biostatistics, School of Public Health, University of Ghana. And he had served as part of the teaching committee in several universities before, including of Florida, University of Gambia, and even Lancaster University in UK. So today he will be sharing his recent research entitled Geostatistical Analysis, web-based mapping and environmental determinants of under 5 chronic malnutrition, stunting, evidence from the 2014 Ghana Demographic and Health Survey. As stunting is a contributing risk factor to child mortality and is also a marker of inequalities, it is of importance how the geographical variation can lead to targeted interventions in specific communities. So we are so excited and honored to have you here with us, Dr. Justice. So without further ado, I would like to give the mic to you, Doctor. Thank you.
Okay, thank you for that beautiful introduction. So I'm just trying to get this. Okay, so thank you very much for the opportunity to share my work with you, and then others who are also very connected to the things I'm doing. It's actually a pleasure. So first of all, I have to thank your university and then your group for giving me the opportunity. On that note, today I'll be presenting on geostatistical analysis, web-based mapping, and environmental determinants of under 5 chronic malnutrition, evidence from the 2014 Ghana Demographic and Health Survey, which is a recent survey. Okay, so this is my presentation outline. I'll give some short prelude, that introduction, the methods, and I'll take it from there. Okay, so the prelude. I know in everything we do, there should be a reason for what you do. So the area that I found myself, especially trying to be the voice for the children, is being actually informed by the period that you are just seeing. And I will just read it briefly. And when you go, you can think about this. It goes, we are guilty of many errors and many faults, but our worst crime is abandoning the children, neglecting the foundation of life. Many of the things we need can wait. The child cannot. Right now is a time. His bones are being formed. His blood is being made. And his senses are being developed. To him, we cannot answer tomorrow. His name is today. So this is something that is very dear to my heart, as said by Gabriela Mistral in 1948. So this is my cornerstone. All that I do today, yesterday, tomorrow to come is based on this ideology. On that note, I'll go straight to the presentation itself now. Okay, so basically, some of you might have seen the map of Ghana already or know something about Ghana, but I just want to take the opportunity to just showcase to you how the map of Ghana looks like. So if you look at the map, to the left of it, we have the Côte d'Ivoire, to the left of it, and then to the top, we have the Burkina Faso, and to the right of it, we have Togo, and then down there, we have the Atlantic Ocean. So these are the countries and the landmarks that borders Ghana. Currently we have 16 regions. By initially we used to have 10 regions, which are the Upper West, Upper East, Northern, Branahafo, Ashanti, Eastern, Volta, Central, Western, and the Greater Accra regions. But now we have 16. Okay. Now, before I move into the modeling aspect, we need also to know something about what malnutrition is all about, and then the scale of the effect at the moment, both at the global level, then at the African level, then also zoom down to Ghana specifically. So malnutrition actually is simply inadequate intake of food, nutrient, or presence of a repeated infectious disease, or both. So what it means is that if you don't receive the right amount of diet, or if you are struggling with some infectious disease that can be prolonged over time, or both of these situations, that you can be considered as suffering from what? Malnutrition. One key thing that we need to know about malnutrition is that it serves as a comprehensive index that can, represent the level and pace of household, community, and then national development globally as well. So it's a very key indicator of health of people. This is something very dear to all of us. And what are some of the consequences if you don't receive the right amount of nutrition? First, there's what you call physical growth retardation, meaning that the rate at which you're supposed to grow, you wouldn't grow at that rate. It also has some effect on your neurological development. One of the things well established is about low intellectual coefficient. And then once you are malnourished, it also increases your morbidity and mortality chances. And then also, for sure, someone who is malnourished, meaning you are ill, you need to be taken care of. So definitely, that also puts some pressure on public health costs, or let me say public health resources that are available in those countries. And for sure, once you are not well, you can be very productive in whatever you do. We were told that, and it has been established in literature, that even if you are young and you suffer malnutrition, this will follow you up to your adulthood and surely will affect your productivity. But the bottom line is that the mortality among this group of children increases exponentially with nutritional status deficiency. So this is something we need to be very worried about. Okay, so these are just some statistics on malnutrition, especially both at the global level, what's happening at the African continent, and then what's happening in Ghana. We'll look at this briefly. So this is not to bother you too much with statistics, but and you actually need to, lay the pace on which I will write with my modeling stuff. So for sure, it has been established that the global burden of under 5 malnutrition is unacceptably high. At the moment, 22.2% of the global children are stunted. And according to the SDG Goal 2 Target 2.2, stunting is one of those things that were considered under that goal, which is to be eliminated by 2030 and to be reduced to international acceptable level by 2025. So the next one too is wasting. That is for instance, when we talk about the stunting, this is what we call the long-term malnutrition in children. Long-term malnutrition in children. That means the children are not growing as they're supposed to grow with time. Then we also have the wasting aspect of malnutrition, which is to do with short-term malnutrition among children under 5 years. Basically, it's looking at your height, your weight relative to your height, and then we're also looking at the underweight, which is a composite score. What it means is that children who are underweight could be maybe suffering from stunting or wasting or both of them. So it is so difficult to separate underweight when it comes to stunting and wasting. Now, for sure, one thing that we know recently is that about 45% of under 5-child mortality in the year 2017 could be attributable to malnutrition in this group of children. And that is something very, very important to us. So nearly half of the under 5 mortality cases were observed globally in 2017 could be attributable to malnutrition in children under 5. Now, when it comes to Africa or sub-Saharan Africa, what is the burden of malnutrition? We know that in 2017, 30.3% of children in sub-Saharan Africa and Africa were actually stunted. And then if you look at the prevalence, this exceeded the 22.2% that we observe at the global level. Then in sub-Saharan Africa also, the prevalence is 33.9%. So what it means is that the stunting prevalence is very high in sub-Saharan Africa, where Ghana happens to be one of the countries. Okay. If you look at the figures I presented earlier, it is very clear that stunting is the one that is the highest. So the current study will focus on stunting. That is why in the next slide, you realize that I was talking more about the stunting. Okay, so how does it look like when it comes to Ghana? Nearly 1 out of every 5 children in Ghana are stunted. And the report we have is that there are regional inequalities in the stunting prevalence across the country. Where in the northern region, we have about 29% compared to the 13% in the Greater Accra region. We also know that the Ghanaian economy lost around 2.6 billion US dollars, which represents 6.4% of our GDP in 2012. In Ghana, malnutrition is actually responsible for 40% of under 5 child mortality. And if you put all these indicators together, it indicates a worrying situation for Ghana and something that we need to work on. Hence the need for some of us who are into the research to do further work to inform policy decisions. Okay. Now I've talked about malnourished children, but I haven't showed you anything, how they look like and that kind of stuff. So in the next slide, I just want to give you some caution that I'm going to show you some sample of children who are malnourished. The graphic might be a bit disturbing to some people. So please, you are warned. Okay. These are just some samples of children who are malnourished, just for your attention. Okay, so why am I interested in this very area or this very study? We all know for sure that understanding the influence of location on health is very critical, especially to epidemiological investigations. Because one of the questions you want to answer is that, okay, so if we come to under 5 child malnutrition, that geographical location matter, that is where a child who is under 5 in Ghana finds himself, would that impact on his or her chances of becoming malnourished or not? So it's one of the questions researchers who are into geospatial modeling will always be asking. That is, how do we link your place of residence to your health outcomes? So in this presentation, my simple task is to be able to link the place of residence of these children to the chance that either they will be malnourished or not malnourished. And here I'm very specific on under 5 child stunting, which we also call chronic malnutrition in children. So it's possible that there could be some evidence already available. For instance, we have some data on the national, regional, and the district level distribution of stunting in Ghana. But one thing that all of them neglected is what we call the localized kind of predictions. That is, for instance, even if you have the predictions at the regional level, the regions of Ghana are so big and that our public health resources are also so limited. So when it comes to universal intervention, it's something that is impractically something you cannot accept. So what it means is that we need to do modeling at levels where even given the limited resource that we have, we can still roll out some interventions to those who need them most. So though there are evidence around the, let's say at the regional, district, or the national level, we need more localized evidence to target decisions. For instance, we're being interested in a particular village or town or city rather than a bigger district level or bigger regional level or the national level as a whole. And for that matter, this study was conducted. Okay, so the methods. What data am I using and what are some of the statistical methods I want to apply to this data? So basically, I use the data from the 2014 Ghana Demographic and Health Survey. And I'm very sure many of you who know about these DHS data because it's being conducted globally all over the places. So we have not less than 120 different countries participating in this DHS survey. and Ghana happened to be one of them. So the data for this study is based on the 2014. The data briefly contains information on maternal and child health, for instance, like their nutritional status using metric measurement. Also, awareness and use of family planning techniques. There's also information on childhood mortality, among others. Now, the data that I'm currently using, during the survey, information was collected on 9,099 women aged 15 to 49 and 4,388 men aged 15 to 59 from 11,835 interviewed households during the survey. The women's questionnaire contains information on children. So based on that, you can extract information on children from the women's questionnaire. So for this study, we extracted information on 2,734 children residing in 415 geographical clusters from the women's questionnaire as indicated. So what modeling technique am I developing to apply to the problem? So basically, in this very study, Bayesian geostatistical methods were used through the binomial model formulation. And it's actually a very simple process. For instance, you can assume yi to be the number of children who are stunted at a particular geographical location. So basically, in the DHS data, we have clusters that are linked to the areas. So we have a cluster serving as the geographical point where GPS codes were collected. So, and in each cluster, certain number of children were sampled from each cluster. So basically what I'm doing is that I will take one geographical location, that is a cluster. Then the next question I'll ask is how many people are sampled from this cluster? So that number of people who are sampled from the cluster will be represented by the NI, the bigger NI. That's the number of people who were sampled from a given cluster. Then at the end of the day, my interest is on, okay, out of this capital big N, how many of the children belong to this capital big N were actually stunted? And that's what I'm using the YI to represent. So it means that in the modeling, my outcome variable is actually the count of children who are stunted. Count of children who are stunted, that is my outcome variable. Okay. Then if that is the case, then once I know my YI and then my capital NI, it means I can produce the empirical distribution of the stunting prevalence at each of these geographical locations. That is the 415 clusters. Because as you can see, I have information on number of children who are stunted at each of those geographical locations. And I have number on how many of these children are sampled from each of those geographical locations. So it's just a simple mathematics where you divide your YI by the capital NY to get your prevalence, which we call the empirical prevalence or the observed prevalence. Okay. So what I try to do is to let SI represent the true prevalence at a given location, XI. So I call that P of XI. That's the prevalence at each of the cluster locations that were sampled. So to analyze the problem, it's easy to assume that once you have the count of children conditional on the prevalence at a given geographical location, this could follow a binomial distribution where you have the total observations to be the capital NI and where you have the prevalence to be P of XI, like I explained earlier. And you just need to take the logic of the prevalence, because remember, I want to predict the prevalence of under 5 child stunting. So I can take the logic of this on a linear scale. So I will have the logic of the P of SI to be equal to the alpha here, which is an intercept term, or you can call it a constant. Then you have some design matrix containing, for instance, if I want to control for any individual level covariate or environmental level covariate, I can do that at this place. So the beta here represent the coefficient of those covariates that I may be interested in. But in this study, I focus on environmental covariate. So the B here, the beta here actually represents the coefficient for those environmental covariate considered in the analysis. And then this quantity here is actually what is bringing in the spatial variability. This is going to take into account this residual spatial information that I want to estimate. This is very important to us. So it means I know that you have a cost standard that does not depend on anything. Then you have something depending on the covariate you're using and something depending on the location that you are considering. Okay. Okay. Right. So as you can see, we have some terms here like the x of s, which is taking care of the spatial distribution. Definitely, we need to know what form is this going to take. That is the distribution of this one. So we'll look at some of these things briefly. I don't intend to go too much into the detail, but I think I need to also let you know how this happens. Okay, so before I can go ahead with my modeling, I need to determine how the correlation of this spatial dimension is calculated. I need to find what you call the correlation function for this, or they can call it the covariance function for the distribution of this spatial quantity. So one of the common and phraseable correlation functions you can think about is what you call the Martin correlation function. So here, I consider the Martin correlation function, which is given as this, as you can see. The sigma square here actually represents the spatial variability in my estimation. That represents the spatial variability. Then you can see a quantity here called K of V. The K subscript V here is actually what you call the modified Boson function of second order. And we also have the V here representing something we expect to go beyond 0, because as you can see, the V could not go beyond 0, then that estimation might not be possible. In fact, the V help out to determine what we call the smoothness of the spatial residual. That is how smooth you expect the spatial residual to be, will be controlled by the V. Then there's another critical element, which is the K. This K quantity here is also very, very important to us in terms of our modeling, because that determines how much differentiable we want to go. For instance, if you have K minus 1 times, we want to see that the K still is more than 0. And also, you can think about the practical range. The practical range simply, we say that is a distance at which the spatial correlation tends to approach what, 0. Or in some papers, they'll say that's a distance at which the spatial correlation approaches 0.1, which means we don't expect any much variability in the spatial quantity. So these are some of the brief ones I want to present. I mean, this is a whole topic on its own, but I know we have people among us who might not be that technical when it comes to statistical issues. So I'll leave this briefly as it is. But it's good for me to show how the correlation function was carried out. And because we actually lack information on reliable prowls, we rely heavily on the default prowls, which is uninformative prowls from the R-inler package that was used to generate or develop the model for this paper. Okay, so how do we implement the model? We follow strictly the Inler approach and then the SPDP approach in our modeling techniques. The reason being that we need to take into account a lot of issues. One, if we are not only interested in doing the prediction at the sample locations, we are also interested in doing the predictions for locations where we don't have any samples taken during the survey, because the goal is to predict continuously over the entire Ghana. So if you want to do that, then you really need to take into account the fact that not all locations were sampled. And for that matter, you need to take into account developing another space where you can map your predictions. So in that way, SPDE came in handy. because we can establish a correlation between the sampled and then the unsampled locations based on the data available to us. And once we're able to establish a correlation between the sample and then the unsampled locations, we can use that to also make predictions, even for the area that we don't have samples taken. Okay, so finally, the implementation was done in the ArtInla software. Now, there is this issue about the web-based mapping and then the exceedance probabilities. For instance, if we want to use our result to inform policy decisions, we have to be sure that our predictions are very informative in such a way that if I finish all this work and I leave my result in a static map, we know for sure that even a single dot with your pen on a static map can represent sometimes a whole region or district or several communities combined. And we are saying that, especially in Ghana, where we don't have enough public health resources to support universal intervention, that we need to develop a process or technique whereby we can zoom down to specific villages where the risk might be high for specific intervention strategies. And that is why we bring in the concept of the web-based mapping. Then when it comes to the accident probabilities too, we're interested in knowing which areas children are more likely to be malnourished. That's one of the things we want to identify. But even that one is still very big, because you might find out that nearly all the places children are likely to be stunted. So we need to quantify how much is that risk. So what it means is that we can sit with policymakers to say, okay, how much prevalence do you want to see before you get worried in order to roll out some intervention? Maybe a stakeholder can say, okay, I want a place where the risk that a child will be stunted is around 30% or 40%. We want that kind of probability that the child exceeds 30% or 40% or let's say 50%. So we can take that into account. Then we can quantify, okay, so if we know this is a prevalence, what's the chance that a given location will have a prevalence exceeding, let's say, 30% or 40%? And that is what this area seeks to do. Then when we achieve that, how do we get a result into the web system where it can support interactive engagement with policymakers? So that is why we perform the web-based mapping and then the exceedance probabilities. So for instance, we estimate the probability based on our Geostatistical model. We can create a probability that the stunting prevalence exceeds that certain threshold. So basically, the first thing we need to do is to use the estimate from the model to find out at what place or at what location is a child more likely to exceed certain threshold, E. So we're using the E here to represent the threshold, as you can see. The XI here is simply indexing the location. And then the E here, the threshold. In this work, we use a threshold of 20% and then 30% to see how the risk is distributed. And one thing we should know from this slide is that if the probability of exceedance, let's say, is close to 1, it tells you that it is very likely that children residing in those locations will have a prevalence exceeding the threshold. Okay, and then if you have the exceedance probability getting close to 0, it's telling you that it is very less likely that children residing in those locations will have a prevalence exceeding the E, which is either the 20% or the 30% that we use in this very work. And then if you have a prevalence very close to 0.5, which is 50%, it is an indication of what you call a maximum uncertainty around that area. What it means is that there's a 50% chance that children residing in those areas will either go below the threshold or above the threshold. So that is what we call a maximum uncertainty. Okay, so as I said earlier, to be able to get our predictions into the web-based system, we made use of the leaflet and then SparseSoft package, all available in R. Okay, so some result from the analysis. Out of the 2,734 children used in this analysis, 535 of them actually were stunted, representing close to 20%. In performing the geospatial models, first we try to find out if without taking into account the special correlation, how the risk factors we are considering look like. And then when we do that, we call that a non-spatial model. When we do that, we observe that aridity, elevation, and precipitation were statistically significant. So that is presented in the table 1. So under the mean, what you're seeing here, these are the log of the odds. These are the log of the odds. Maybe if you're interested in the odd ratio, you can just exponentiate these ones and you get the odd ratio. Then we have the log of the odds with the associated 95% Bayesian credible interval. So here the 2.5%, that is the 2.5% quantile, and this is 97.5% quantile. Putting the two together gives you the 95% Bayesian credible interval. So as you can see, the aridities, like I said, and then the elevation and precipitation were significant. You could not see the temperature being significant here in the non-spatial model. Surprisingly, when you go to the spatial model now, that's when we are taking into account the spatial correlation. That is the effect that, in fact, geography or geographical location should have some effect on our outcome. Whereas none of these 3 significant covariates were significant anymore in that model. So this is a Bayesian geostatistical binomial model that we fitted. Still, the mean is actually the log of the odds, and then the 95% Bayesian credible interval remains the same. Here you can see that none of the risk factors that were even significant in the non-spatial model were significant here. What it means is that taking into account the geographical locations of these children, we have been able to explain even the differences the statistical differences that we observed in the aridity, the elevation, and precipitation variables. For that matter, they are no more. Okay. Right. So now the core element in this work is the spatial predictions. So the next thing I'm going to show you are the various maps that we have developed based on these results. So I'll show you predicted prevalence with their 95% Bayesian credible intervals. I'll also show you the web-based interactive mapping based on the same estimate. Then we also will look at the accidence probabilities. And as I said earlier, this is based on 20% and 80% accidents. Then what are some of the statistics around my model? That is, I need to quantify the variability in my estimate. So we also produce the maps of the standard error across the entire country to observe this. Okay, so first of all, definitely I need to show you where the samples are coming from and how the empirical prevalence of stunting looks like. So I will go to that place straightforward now. So the map you are seeing now is the study locations plus the empirical prevalence of stunting. So all the circles represent areas where samples were drawn in Ghana for the survey. So basically, these are the cluster locations of the children. These are the cluster locations of the children where samples were taken. Then the colors that you are seeing represent the prevalence. That is empirical prevalence. So here is just the raw prevalence that we are looking at. It ranges between 0 to 1. And then you can look at some few variabilities in the prevalence. It looks really random, but we'll go further to look at this in the web-based application. So now, as I said earlier, even a single dot like that, if you take each of these circles, this could represent several communities combined or a district or something. So we need to develop a process where we can go down and look at this. And that is why you can see some Google icon. Please, can you see the Google icon here on the right? I need a response to this one because I'll be using this. Can anyone confirm that they can see the Google icon on the right of the map?
Yes, we can see the Google icon, Doctor. Yep.
Great. Thank you. So this is a web-based version of the static map that you are seeing. So if I'm interested in this, all I need to do here is to click on this, and it will take me straight to the web to have a look at what's happening over there. So I try to click on this one. Before I can go there, I will need to move away from the presentation mode and then come to this mode, and then just double click this one, and it will ask me if I want to go online to check this. And if I say yes, it will take me to the web where I can interactively play with this naive or empirical prevalence of stunting. So as you can see, it's loading. So it's not asking me to open. So I'll just click on open, and then it should take me to the web quickly. Please, can you see the current screen?
Unfortunately, we're still seeing your slide presentation, Doctor.
Okay, that's fine. So I'll just stop this one and just share the other one quickly. Web. Just a moment. I want to share the new screen. So just a moment. Okay, please, can you see it now?
Yes, now we're seeing the map now.
Yeah, okay, that's good. So the question is, what is the use of this kind of system? So as I'm here, I'm in the web now. What I can do is to expand this map slowly, trying to identify specific locations in Ghana where the risk might be high or could be low. So you can see these things here. These are rivers in Ghana. So you have taken into account the rivers in Ghana in our modeling so that we don't produce predictions for areas where there are rivers. So that has been taken into account. Now, if I come to a place here, if you look at, there's a yellow sign here, and you can see that the yellow ranges between 75 to 100% prevalence. So if you look at this very area, I can see the nearby town I can see at the moment is Mandai, but I can zoom out on this yellow to see which towns are very close to this yellow icon, which stands for a very high prevalence location. So this is what the use of this interactive web-based map is all about. All you need is a very strong internet connectivity, and you have access to specific locations. But this will be very much easy when we get to the actual prediction. So this is purely just to showcase how the prediction works like. So that's the sense of doing the web-based system where you can interactively zoom out or zoom in on particular location just to see what is happening. So on this note, I'll move from this one now and then go to the presentation slide. Okay, I hope we are back onto the initial slide. Are we back onto the initial slide?
It's loading. Oh yes,
Okay.
yeah.
Okay, so that's it. So quickly now, we're almost done. This is the predicted stunting prevalence based on our Bayesian geostatistical binomial model. So the prevalence ranges from about 4% to about 45% in the population of Ghanaian children under 5. So you could see that there are certain locations where the risk seems to be very high, while others it seems to be very low. For instance, this is a northern region of Ghana, which is always known for these situations. You could see that the predicted prevalence is very high. most of the areas ranging between about 37% to 45%. And then, but when you come to the Greater Accra area here, which is this place down, that's close to the ocean, Greater Accra here, you could see that, I mean, the chance of somebody getting stunted is very low here. Also, some parts of Ashanti region and the Borno have also observed some, I mean, low prevalence anyway. But still, as I said, this is still not too useful for policymakers. So as you can see on the right side, you can again go to the web and see these and actually interact with this one-on-one and zoom down specifically to communities where the risk is looking very high. I will just do for this one, and then the other one maybe is the same strategy. So let me do for this one, and then we quickly wrap up. So again, I'm trying to open up the web-based prediction for the stunting prevalence. So I'll stop sharing this one. Okay, it's loading, so I'm going to share in a few seconds. Okay, that's fine. Okay, so go and share. Chrome. Okay, please, can you see the current map now?
Yes, I can confirm that we can see it now.
Good, thank you. So as you can see, it's the same prediction that we are able to move into the web-based application so that we can easily expand the map to see which communities are more likely to be hot stunted. So these are predictive stunting map. So as you can see, we're able to put Ghana in context. So this is a physical world map where you can locate where Ghana is. And then I can now zoom out on specific communities where the risk appear to be high. Again, I'll focus on the northern part of the country, but that is where we are having the problem as far as the high prevalence of stunting is concerned, based on this map. So I'm just trying to zoom up. Okay. Please, this is internet dependent. So once you are zooming out, it will take a bit of time, but it will soon arrive. Okay. So as you can see, I can see one town here called Yeji. Yeji is actually one of the towns in the northern part of Ghana. You can see clearly here. So it's one of the towns that are very close to areas where we are likely to observe a very high stunting prevalence. And there's another one at the top here, that is Magongo. Magongo is another community where you can see that the prevalence is also very high. So this is the essence of developing, this is just to showcase the essence of developing the web-based application. So now this is a specific town. If somebody wants to roll out an intervention, it's easy for you to go to this specific town and roll out your intervention for the town. Okay, compared to the static map that you see, where we cannot tell which town exactly we're suffering because everything is condensed at the same place, and you cannot tell where they belong. So I mean, do this for several other towns just to see how they also compare when it comes to the prevalence of stunting in Ghana as a whole. But because of time, this is just what I want to showcase. So I can search across the whole of Ghana to see how the stunting is looking like in each of specific towns and other smaller locations. So I will just go away from this now and go to summarize my presentation. Please, can you see the new slide now?
Yes, now we
Am
can
I
see.
back? Am I back to? Okay, that's fine. Thank you. I'm trying to put it in a PowerPoint presentation mode, please. Okay, so this is a predicted stunting prevalence in Ghana, and then
I
this
think
is what we call
we
the.
cannot see the presentation at the moment. The,
Okay, sorry,
sorry
sorry.
about that. Yes.
Yeah, sorry. Um, please, can you see the presentation now?
Yes. Now we can see it. Thank you.
Okay, thank you. So this is the one we have just looked. This is a predicted stunting prevalence in Ghana. So we try to also quantify the uncertainty around it using the 95% Bayesian credible interval, and that will be the next slide. So this one is the lower 95% Bayesian credible interval. That's the predictions. These are the predictions. The lower Bayesian 95% credible interval, and that will range from about 0.1 or something up to 0.336. So that is a lower predicted prevalence based on the 95% Bayesian credible interval. Again, it's the same northern part that is showing the high risk. And then if you go to the upper bound, that is the upper 95% Bayesian credible interval to similar trend exists. But that one ranges between, let's say, 8% up to close to 63%. So it helps us to also measure the amount of uncertainty around our predicted estimate. Then, of course, we also need to work on the exceedance probability. So the one you are seeing over here is measuring the chance that a given child at a given location will exceed the prevalence of 20%. That we are doing in this case. Again, some few places were picked up. So these are the locations where, I mean, the deeper areas are the locations where the chance that a child will prevalence at a particular location will exceed 20% is very high. Okay. And where you have lighter areas are the areas where the chance that a given child at a particular location will exceed 20% is very low. And where it is close to 50%, that's a high uncertainty. Okay, so this is why we try to find out how about if we want to find out the prevalence exceeds 30%, how would it look like? And this is the distribution of it. So majority of the areas in Ghana here seems not to be at high risk when it comes to prevalence exceeding 30%, except in the northern part of the country, as can be observed. Okay, so this is the standard error of our estimate. And then you could see that it ranges between 0.0177 up to 0.08993. So this is telling us that even our standard error throughout the prediction are below 1, as suggestive of a very reliable and a very good precision for our estimate. But you can see clearly that, okay, before you can actually what was happening is that areas where the data seems to be, I mean, the coverage is very low in terms of the data that we have used. They seems to have higher standard errors, relatively higher standard error compared to where we have a lot of data. So that's just to show you again the location map. As you can see, if you look at these areas, there's a lot of places here where we don't have data collected, like these areas. So if you also look at how the standard errors were distributed, the standard errors were very high at areas where we don't have much data. So this is just what I want to point out to you. But nevertheless, the standard error on the whole is all of them are below 1, suggestive of a good precision for our estimate. Okay, that's some key findings. So in the non-spatial model, we know for sure that reality, elevation, and precipitation were helping to influence the outcome, but that was not the case in the geospatial model. Then we realized that, in fact, if you go to a certain part of another region, the chance that a child will be stunted is very high. And then we also observe relatively low standard errors for our estimate. suggestive of precise estimate for predictions. And then we know for sure that this method can actually help to support policy decisions. So in conclusion, geostatistical modeling method supported with interactive web-based tools and more localized predictive maps can help target limited public health resources to stunted children who needed it most. And we advocate for greater consideration to be given to the high-risk areas identified in terms of resource allocation, policy, and intervention strategies. For sure, we recommend some further studies in the form of qualitative research to identify why certain geographical locations are experiencing very high stunting prevalence compared to others. On that note, I'll have some acknowledgement to make. Actually, I did this work during my fellowship with University of South Florida College of Public Health under the host of Professor Atachu Dakni. And then the fellowship was also sponsored by University of Ghana Building a New Generation of Academics in Africa project. And the data was freely provided by the major DHS program from USA. I have some references for you for those who might be interested. And thank you.
Thank you so much, Dr. Joseph, for that very interesting and interactive presentation. So we can see that there's quite a very significant spatial and geographical differences between the stunting in Ghana. So there's a few questions from our participants tonight. There's 3 so far in the chat room. So I'll start the first one. The first question is from Professor Kim. He's asking Dr. Aheto, how big the size in meaning the participants for each cluster?
Okay, let me just go there and then I'm trying to go to the chat room myself. Okay. Okay, so the YI is the number of stunted children at each cluster locations. Hello, Prof. Suhala. Hello, please, can you hear me?
You're asking for, sorry, what was your question, Doctor?
No, I was saying that the YI represents the number of stunted children at each of the selected clusters. Hi, Kim. I'm good. Yourself? Good to see you too. In fact, I must say that Kim happened to be my mate at Lancaster University in the UK when we were all doing our PhD program. Nice to see you, Kim. Okay, I think that's a good question. In fact, I can't remember the number of, in fact, we have a good number anyway for each of the clusters, but I can't immediately just tell you how many are there for each of the 415 cluster locations. But in fact, we have a lot of observation because the reason being that in each cluster, the survey will collect data on at least approximately 30 different households in each cluster. Then from these clusters, women within the reproductive age, 15 to 49, are sampled. Then all children under 5 in those households are included in the survey. So we can do some calculation whereby we can divide. I think the total number we use is 2,000 and something. We can divide that by the 415 to see that approximately what is the average. So we can do that right away. Yes. So let me just do that. Yeah. elevation, precipitation, temperature. Yeah, yeah. Yes, thank you very much. So, in fact, for this particular study, we did not take into account individual level covariate, except the environmental covariate. But the reason being that we were actually key on how environmental factors on their own could influence the outcome. But another improvement is to allow for individual level covariate. I agree for sure. And that is exactly what we did for the one for under 5 mortality. So if you have a look at under 5 mortality, realize that we have taken into account both the individual and then the environmental covariate in that model that was published recently. Thank you. But for this very one, we did not take into account the individual covariate. Yes. I'm grateful, Kim.
Yes, good afternoon here. Can I ask a question?
Yes, please.
Sorry, yes, please.
Yes, this is Karim. I'm sure you might know me.
Oh,
It's
hi,
one of
Karim.
your,
Yeah, yeah.
yes, thank you. Yes. Actually, I was following and looking at the logistic regression you have used, and I was trying to understand the outcome variable, which is the standard, which is let's say
Okay,
the binary. Okay.
okay.
But as the just the previous questioner,
Yeah,
I was thinking you could have maybe some intrinsic variables
okay.
include to the environmental variables so that when you
Okay.
are doing a prediction or you're trying to look at the outcome, it will not only be on the environmental factors, but it will also contribute to that of the instructive variables, such as the, let's say, the age of the mother, even the sex of that particular person of the
Chat.
child, either it's a male or a
Mm-hmm.
female,
Mm-hmm.
and let's say maybe even the faith or the religion. All those things could be factors that account for the standard or not. So I think
Yeah.
maybe it would be a very nice maybe study if we could include these factors maybe for further study.
Yeah, okay. Thank you very much, Karim. I think this is a genuine concern from everyone because the more you're able to take individual information into account, the better. The only thing is that you see the modeling approach that we have used here, which is very novel, is that this is not a Bernoulli kind of outcome. Okay. For instance, if it's about the Bernoulli outcome, what you guys are saying will have been done much easier because this one you're dealing with the individual outcome, yes or no, and then you are looking at how the environmental and then the individual level covariate influence that, and then you're taking also into account the special, geographical information. Okay, that is excellent. But this one, we actually counted number of children residing at each of the clusters. So if I want to even use the individual level covariate, I have to make sure that I aggregate those information at the cluster level. For instance, if it's about sex, I can do like proportion of males who were actually within that cluster. Okay, so I'll be using a proportion rather than the individual information. Okay, so that can be done. So I agree. What I need to do maybe in the next work I'll do that is related to something like this. I could generate the proportion of, for instance, if it's about yes or no, or maybe about sex or something. I can calculate the proportion of somebody or proportion of children who are maybe age below 5 years, or sorry, age below, let's say 2 years, and they use that in a modeling. At least that will also explain some information when it comes to the effect of the age on the outcome. That will explain it. Or when it comes to maternal education, for instance, I could find a proportion of mothers who had at least primary education or secondary education. Then I can use that proportion in my modeling because definitely once I'm doing the analysis at the cluster level, I need to aggregate all the information at the cluster level to be able to make predictions. And another danger is that after fitting the model, you also require information that are in the model to be at locations where you don't even have a sample taken. Okay. So for instance, if for sure where the data were taken, the samples were taken, we'll certainly have information at those locations. But how about the locations where the samples were not taken? How do we have information on the child age at that location where information is not collected? So what it means is that we first need to aggregate information at the cluster level, and then based on that, then establish the correlation between the cluster level and then the non-cluster sample levels, and then do the prediction. So I agree that the more information we have in the model, at the individual level also can help us improve our predictions. I agree on that one. But these are some of the possibilities ahead of time. Thank you.
Thank you very much. Thank you.
So any other questions from the participants? Okay, I'm guessing that there's no more questions from the participants. As a representative from all the participants, I would like to thank Dr. Aheto for the presentation. And before we end this webinar, I would like to call upon Prof. Kim, Prof. Kamal Iman, to give his a few words to Dr. Aheto.
Thank you very much. In fact, I must say that I'm very grateful for the opportunity. And when it happens like this, we learn a lot from each other. And I'm ever available for us to collaborate on similar projects. And together we can fight a common goal that is aimed at improving health among populations. So thank you very much for having me. Thank you. Grateful.
Thank you so much, Professor Kim. So thank you again to Dr. Justice Aheto. So with that, I would like to end this webinar for tonight, and we would like to invite to thank all participants for joining us until the end of the session. So hopefully we will see you again in the next webinar from our epidemiologic and statistical modeling from USM. Thank you so much, everyone. Good night.
Thank you. Good night.
Bye-bye.